Welcome back. Chapter 8 Estimation. Section 2.1 Estimating mu when sigma is known. Sigma stands for standard deviation, mu stands for mean. So, in this section, we are going to learn about estimating the mean when standard deviation is known. Notice these are population parameters. So, the focus points in this particular section are explain the meanings of confidence level, error of estimate, and critical value. Okay, we will see what these things mean. Find the critical value corresponding to a given confidence level. Compute confidence intervals for mean, mu, when sigma is known. Interpret the results. Compute the sample size to be used for estimating a mean mu. Okay, let's see what these things mean. Estimating mean mu when standard deviation sigma is known. Because of time and money constraints, difficulty in finding population members, and so forth, we usually do not have access to all measurements of an entire population. Instead, we rely on information from a sample. In this section, we develop techniques for estimating the population mean mu using sample data. Okay, so using sample, we want to say something about the population mean. We assume, so here is an important assumption, we assume the population standard deviation is known. So we are assuming sigma is known. Now, let us begin by listing some basic assumptions used in the development of our formulas for estimating mu when sigma is known. Assumptions. All right. First assumption. We have a simple random sample of size n drawn from a population of x values. All right. So our sample is simple random. All right. And we have fixed a size m. We know the value of sigma, that is the population standard deviation of x, is known. Here is another very important assumption. We assume that our population x, random variable x, distribution is normal. If it is normal, then the methods work for any sample size. If it is unknown distribution, okay, so we don't know x has normal distribution, then we require sample size to be at least 30. Greater equals 30 means 30 or more. However, if the x distribution is distinctly skewed, so we don't know anything about x, well, you need at least 30. But if you know that the distribution is distinctly skewed and definitely not mound shaped, you need a sample size of 50 or even 100, or higher may be necessary. Okay. Now, an estimate of a population parameter given by a single number is called point estimate for that parameter. So to begin with, you're looking for an estimate. Estimate of a population parameter given by a single number is called a point estimate for that parameter. It will come as no great surprise that we use x bar. It should be x bar. Okay. The sample mean as the point estimate. Okay. For mu. So we are going to use the sample mean as a point estimate. All right. A point estimate of a population parameter is an estimate of the parameter using a single number. That's a point estimate, a single number. All right. So we cannot say, okay, I'm estimating the population mean to be between 50 and 60. Now that is not one point. All right. you are giving me 1 point, and that one number is x bar. X bar is the point estimate for mu. Even with a large random sample, the value of x usually is not exactly equal to the population mean mu. That x should be x bar. Oh, there you go. Okay. The value of x bar is usually, so the sample mean is usually not exactly equal to the population mean. There is a margin of error. The margin of error is the magnitude of the difference between sample point estimate and the true population parameter value. So magnitude means absolute value. You see, your estimate might be higher, might be lower than the actual or the true population parameter. So you don't want margin of error. People don't like to think of margin of error to be negative. So that's why you take magnitude or absolute value of the difference. When x bar is a point estimate for mu, the margin of error is the magnitude of x bar minus mu. So if x bar is smaller, I don't want a negative number, so I take absolute value. We cannot say exactly how close x bar is to, it should be x bar, there you go, right? So x bar is to mu when mu is unknown. All right. Therefore, the exact margin of error is unknown. We don't have an exact value here because we don't have mu. All right. Of course, mu is usually not known, or there would be no need to estimate it. In this section, we will use the language of probability to give us an idea of the size of the margin of error when we use x bar as a point estimate. So we want to use probability basically, all right? You will see in a minute, okay, what that means. First, before we go there, let's learn about confidence levels. The reliability of an estimate will be measured by confidence level. All right. So confidence level. So if you tell me you estimate the average income in New York City to be, I don't know, $105,000, okay, yearly income. Now, I'm going to ask you, how confident are you? 105,000? How do you know it's higher? It's not higher, or it's not lower, so on. So you have to give me with a certain confidence level. So that confidence level that we understand in English has to be written down on paper in mathematics or in statistics. So if you want a certain confidence level of C, for example, I'm 90% sure. 90% means 0.9. 95% means 0.95. 99% is 0.99. All right. So you want to give me that number, confidence level. Okay. Theoretically, we can choose your confidence level to be any value between 0 and 1. You can say 0%, but that's hardly confidence building, right? And 100%, well, that you should really know something more than you're telling me, right? To say 100%. But usually, C is between, confidence is between 0% and 100%. And to have a good confidence level, typically people take 90% or 95% or 99%. So your number C could be 0.9, 0.95 or 0.99. So let's look at this picture. So remember this. This is your normal curve. Standard normal curve means 0. You want this probability to be your confidence level C. You need to find that number and its symmetric number, that number, okay? So that number is called critical value. ZC is called critical value. All right, let's continue. In each case, the critical number ZC is the number such that area under the standard normal curve between negative ZC and ZC is equal to C, your confidence level. The value ZC is called the critical value for a confidence level of C. For a confidence level C, the critical value ZC is the number such that area under the standard normal curve between negative ZC and ZC equals your confidence level C. Remember, confidence level is a number. It's not anymore percentage. It's a number between 0 and 1. The area under the normal curve from negative C, from what? From ZC to negative C. Okay, so something is missing there. From ZC to negative ZC is the probability that the standardized normal curve Z lies in that interval. So basically you're looking at probability. Your standard score lies between negative C to ZC. Negative ZC to ZC. That probability has to be C. Okay. So this is good. We use standard table because we can use standardized scores so that we can use our tables. Okay. Now this is where you can find table. So if you want to find a critical number for 99%, so you want probability to be between. You want the probability where your Z score is between these two. So you want that. So question is to find the critical number. We saw how to find Z value when we were given an area between two numbers. Well, you want to find corresponding area to the left of negative C. So let's figure out. You see this is 99%. So you have 1% left over here and here. 1% split equally. So if 1% is split equally in these two regions, 0.5% is the left area. 0.5% comes to 0.005. Okay. So using your table, you need to find that value for which area to the left is 0.005. If you look at the area table, you will find 0.0051 and 0.0049. Think of it, suppose you didn't have the decimal points. This is $51. This is $49. You want precisely $50 right in the beginning. So it's going to be negative 2.575. Okay, right in the beginning. Negative 2.575 is what we get using the table. But let's see what they say. Okay, they are saying it's between negative 2.58 and negative 2.57. Okay, so they are choosing something even wider. Okay, they are not choosing exactly 7.5. Why would they do that? They are choosing something wider, farther. Why? Because if you're farther, right, if your Z is farther to the left, then you will get more area in between, because this guy, negative guy, will be farther and his symmetric guy will be also farther. So you're guaranteed to get 99% here. All right. So that's a subtle point. If I use the table, if you remember, we were getting negative 2.575, but they are taking a rather conservative estimate. Okay. Next part of the slide will continue in our next video. Until then, bye.